Homework 10, Quadratic Functions, Video 3. In the previous video, we talked about how to find the vertex of a quadratic function that is in general form by using the formula -b over 2a for the x-coordinate and inserting that value into the function to get the y-coordinate. Granted, it was a little bumpy because we had fractions, but it's just a fraction. So how do we find the vertex of a parabola whose function is in standard form? Well, you might be thinking, don't show me another way, I'll just do that. Well, you can, but before you do, make sure you're in the correct form. The only time to use this formula for the vertex is when your function looks like this. Has an x squared term, has an x term, has a constant, and no parentheses. This function has parentheses and does not have an x squared term and an x term. You could argue it has an x term, I would argue it's squared. But it has parentheses, so it's still not going to look like that. So can we make it look like that? Well, you could. What if we did try to make this function look like general form by eliminating the parentheses? To eliminate the parentheses, you have to remember that squaring something means to multiply by itself. So we're going to multiply the x minus 1 times itself. Don't forget the plus 7. Then we have to FOIL this. The -3 is still there. I will spare you the details of the FOIL process. X squared minus 2x plus 1. And now we have to distribute the -3. -3x squared plus 6x minus 3. Don't forget the plus 7. And now we have like terms to combine. -3x squared plus 6x plus 4. So we can manipulate it and transform it from standard form into general form if we're going to use that approach. So let's see what happens if we do. Remember, the formula for the x-coordinate of a parabola whose function is in general form is -b over 2a. The b in this function is the coefficient of the x, so it's 6. It picks up a negative. The a in this quadratic function is -3. So in the denominator, it gets multiplied by 2. So we have -6 on top of -6, which is just 1. Okay, that's looking promising, because now to find the y-coordinate, I just have to insert the x-coordinate into the function. Now, we can insert it into the general form or the original standard form. We might as well use the general form again. -3 times quantity 1 squared. So square the 1, not the -3. Plus 6 times 1 plus 4. Please excuse my dear Aunt Sally, exponent happens first. 1 squared is 1, and then -3 times 1 is -3. Plus 6 times 1 is 6, plus 4. 6 plus 4 is 10, and -3 is 7. So the vertex is 1, 7. So you can find the vertex by eliminating the parentheses, converting the function into general form, and then using the vertex formula for general form. But do you notice anything about the answer? Our vertex was 1, 7. Look at the original function in standard form. Notice anything? There's a 1, and there's a 7, and the vertex was 1, 7. Was it a coincidence? Of course it wasn't. In the first video, I mentioned that if I invented math, I would have called standard form vertex form. And the reason is, the vertex is embedded in the form. So although this will work, it sure is spinning a lot of wheels to grab two numbers that were there in the beginning. You do have to be careful though. The two numbers in the vertex aren't exactly like the two numbers in the beginning. The 7 is. The 7 was positive, and so is that one. But in the original function, the 1 was negative, and now the 1 is positive. So there is a small place to be careful when you extract the vertex from standard form. So I'm going to erase all of this work that we just did, not because it was bad, but I wanted to show you that there's two ways to get the vertex out of standard form. One is to smash it open until it looks like general form, and then use the formula for the vertex of general form. But you're wasting a lot of time because standard form contains the vertex inside of it. So it's not really a formula, it's an observation, and it goes something like this. The vertex of f of x equals a times parentheses x minus h close parentheses squared plus k is h comma k. And if you'll notice, the signs behave the same way as they did before. The number in the parentheses changes signs. It was a -1, but in the vertex it was a 1. It's a negative h, but in the vertex it's an h. And the number at the end doesn't change signs. At the end it was a 7, and it's still a 7. At the end it's a k, and it's still a k. So the vertex is embedded inside of standard form. You just have to remember, the number after the x comes out and changes signs. The number at the end comes out and doesn't change signs, excuse me. Believe it or not, it's consistent. But one changes signs and the other one doesn't change signs. Why is it consistent? What I'm about to show you isn't necessary to know. So after you watch it, if you're like, I was good until then, forget it happened. The reason it's consistent for this number to change sign, but not that one, is because of the variable y over here. I know we don't see the y, but f of x is just a fancy name for y. If I move that 7 from the right to the left and put it after the y, it becomes a -7. And so here's the consistency. In an equation, when you add or subtract a number to a letter, it moves a graph in that direction, but the opposite of what you would expect. For example, if I subtract 1 from the x, it moves a graph in the x direction, but the opposite of what I expect. I expect it to go to the left, but it would go to the right 1. If I subtract 7 from a y in an equation, it moves the graph in the y direction, but the opposite of what I expect. Moving in the y direction, I would expect a -7 to go down 7, but it's up 7. So it's actually consistent that the number after the x changes signs, but the number at the end doesn't change signs, because the number at the end describes a movement in the y direction. So if you put it on the other side with the y, then it too changes signs when it comes out. Like I said, if you were good up until there, then forget that last minute or so just happened. To find the vertex in standard form, pull out the number after the x and change its sign. So if it's negative, it becomes positive, but if it's positive, it becomes negative. And for the y coordinate, just grab the number at the end, but don't change its sign. Pretty straightforward. Oh, there is one other thing I meant to mention in the previous video, so I'll go ahead and mention it now. I mentioned that some parabolas open up and some parabolas open down. I always take this for granted, but there's a clue in both forms of a quadratic function that predict which direction it opens. And as you may already know, it's the a. If your a is positive, your parabola opens up, and if your a is negative, your parabola opens down. If you're positive, you're smiling. If you're negative, you're frowning. That was corny.